Hello, everyone. Today, I'm delighted to share our work on estimating perceived accessibility of desktop applications. I'm MD Touhidul Islam, and my co-authors are Dr. Donald E. Porter from University of North Carolina at Chapel Hill, and my advisor, Dr. Syed Masum Billah. I'm going to start the discussion by talking about two terms that are commonly used to measure the user experience in an app in HCL literature. They're usability and accessibility. Usability measures to what extent the software offers effective, efficient, and satisfying user experience. Traditionally, usability is measured in terms of completion times of certain tasks, such as navigation in an app. Accessibility indicates, on the other hand, to what extent the software can be used by people with various disabilities by assistive technologies. Accessibility is commonly reported by how many accessibility guidelines from a given standard, such as WCAG, an application violates. Although closely connected, usability and accessibility does not entail one another. For example, a piece of software, such as remote desktop clients, can be usable to a particular user group, such as sighted users, but can be inaccessible to another, such as blind users. Conversely, a particular user group, such as blind users, can access the software via assistive technologies, but their experience can be poor. In this paper, we first investigate the contributing factors in accessibility and usability from blind users' point of view when using desktop applications. To do that investigation, we performed a study with 11 expert blind student users. We imposed this constraint because prior research has shown that usability models constructed with expert behavior can well approximate outcomes across a range of visual tasks and devices for general users. Our interview questions focused on, firstly, the understanding of important qualities of an accessible app. For this purpose, we asked questions such as, what is accessibility to you? What do you mean when you say an application is accessible? And what is your view on accessibility? We also wanted to see how participants rate different applications based on their accessibility and usability. As such, we asked them to rate commonly used applications on a scale of 1 to 5, with 1 being least accessible and 5 being most accessible. Finally, we collected some application-specific usage data to understand what percentage of the feature participants typically use in an app, and what is the maximum number of keystrokes they're comfortable with when performing a navigation in an app. Our findings show that participants rated Notepad, Calculator, and Microsoft Excel as the most accessible apps. They consistently rated Visual Studio as the worst. When looking at the percentage of features used in an app, we see that most participants use less than 20% features in Microsoft Word, a number which we were all surprised with. As for the maximum number of acceptable keystrokes, most participants reported 3 or 4. As for our investigation into what constitutes accessibility and usability in an application, we discovered several factors. We use the term perceived accessibility to represent the experience of blind users while using an app. Participants reported that the perceived accessibility of an app depends on the ease of keyboard navigation. In other words, fewer number of keystrokes they need to use. They also mentioned the ability to use the app on one's own without requiring help from sighted individual. This is also connected to ease of navigation, as performing simpler navigation is less likely to result in needed help from someone else. And then there was also the ease of understanding, learning, and explaining it to others. Finally, the reliability of keyboard shortcuts. In other words, they want consistent shortcut behavior across applications, such as Ctrl+C for copying in all apps. This is also related to navigation. Based on all the above findings, we identify ease of keyboard navigation as the primary contributing factor to perceived accessibility of an app. Next, we model keyboard-based navigation. On the left is a screenshot of a menu in Notepad. Different menu options are marked with the alphabets A to J. On the right is a graph representing the UI, and the screenshot on the left. Each node in the graph represents the UI item on the left. Let's consider that our goal is to navigate from node A to node I. Both are marked in green color. The green arrows on the graph shows the optimal travel path from A to I. If each hop takes 1 keystroke, we can say that this navigation will take 7 keystrokes. In other words, the cost of this navigation is 7. The purpose of the cost model is that it calculates the cost of every possible transition in the app hierarchy. Going back to the notepad example, let us select only 3 nodes, C, E, and I for simplicity of figures. The new complete graph on the right shows the cost model for only nodes C, E, and I. The numbers along each edge represents the cost of the transition associated with the edge. The transition model assumes the probability of every possible transition in the map. Now, the probability distribution can be of 2 types. The first is uniform probability distribution, where each transition is equally likely. Again, let's select nodes C, E, and I for simplicity. The figure on the left shows the transition model with uniform transition probabilities. Given there are 6 possible transitions, the probability of each transition is 1 by 6, as shown by the calculation on the right. However, in real-life usage, not all the transitions are equally likely. To address this phenomenon, also facilitate user-specific probability distribution. In this method, all the nodes are divided into 5 buckets based on their likeliness of being visited by a user. The user specifies the nodes they visit the most, the nodes they never visit, and so on. Then, we adjust the probabilities of all the transitions leading into the nodes according to the bucket they're in. This is done using a staircase probability distribution. For example, bucket B0 is called the never bucket, and the probability for this bucket is set to 0. Bucket B4 is the most likely bucket, and the probability for this bucket is set to maximum. Now we derive some metrics from the models we described. The first metric is called complexity, which is the expected number of keystrokes to perform one transition in that. Going back to our notepad example with nodes C, E, and I, we can calculate the cost of one transition using the formula of mathematical expectation. The cost of each navigation comes from the cost model, and the probability of each navigation comes from the transition model. For example, the navigation from C to E has cost 2 and a probability of 1 by 6. After calculation, we find that the complexity of a given scenario is 3. The next metric is n keystroke coverage. It stands for the fraction of all possible navigations that can be achieved within n keystrokes. By dividing the number of edges with costs less than 3 by the total number of edges, we can get the 3 keystroke coverage. So we're calculating 3 keystroke coverage here. We can see that there are 4 edges with cost less than 3. So the 3 keystroke coverage is 66, around 67%. The final metric is X% reachability. It stands for the number of keystrokes it would take to cover at least X% of all possible navigations in the app. With our notepad example again, let's say we wish to calculate 20% coverage. We can create a table with the percent coverage for each number of keystrokes. It's evident that we would need at least 2 keystrokes for 20% coverage. Use cases of our proposed metrics. The first use case would be analysis of commonly used applications. Lower complexity, higher and keystroke coverage, and lower X% reachability are desired for an app. We can see a drastic difference in values between the values with shortcuts and without shortcuts. To understand the metric values for different, if the metric values for different apps make sense or not, we conducted a follow-up interview with the same set of 11 participants. We mainly asked 2 questions. If the complexity scores match their real-life experiences and their views on learning shortcuts given the large difference in complexities with and without shortcuts. Most participants generally found the scores representative of real-life scenario. One participant said, for Word, those scores make absolute sense, both numbers. They have huge objective insights and are very believable. Another participant had this to say about Microsoft Excel. 22 and 16 keystrokes without and with shortcuts. Yeah, that is accurate. Sounds like Excel. Another use case of our metrics would be optimizing UI hierarchy. Let's say our goal is to maximize the 3 keystroke coverage while adhering to constraints mentioned in the second column of the table. On the left is the original configuration. Using the goal and constraint on the table on the top, we can use a simple Python optimizer to get the optimal hierarchy, which is shown in the middle. On the right, the table shows the before and after costs for each transition in the hierarchy. Other possible uses of our metric would be detection of hard-to-reach nodes and evaluating multiple navigation designs such as linear versus circular navigation. Speaking of the usage of our metrics, participant P8, who is an assistive technology trainer, said, I wish I could tell the people I teach about these numbers. They will help them in the decision of choosing, using, and in-depth learning of an application. To wrap up, low navigational complexity is crucial for blind screen reader users, and it contributes to their perceived accessibility in an app. This paper attempts to capture this perception using a probabilistic model. Next, we derive through metrics which reveal important statistical characteristics of an application. These metrics can be useful for blind users, application developers, and accessibility practitioners. Thank you for listening to this presentation. And if you have any questions, please reach out to me at mqi5127@psu.edu. Thank you.